Hello, I'm Harsh. Today I'll be presenting our work, UMI-on-Air, a collaboration between Carnegie Mellon University and Stanford University. UMI-on-Air is a framework for aerial manipulation. It begins by collecting large-scale demonstrations using the Universal Manipulation Interface, or UMI, to train embodiment-agnostic visuomotor policies. At deployment time, we guide these policies with embodiment-aware feedback, enabling aerial robots to perform challenging real-world tasks. But this raises a key question. What is embodiment-aware guidance, and why do we need it? Not all robots can perform UMI policies equally well. Embodiments like Oracle, a perfect flying gripper, or a standard tabletop manipulator, such as the UR10E arm, have high UMI ability. They can track policy trajectories accurately and achieve strong performance. In contrast, unmanned aerial manipulators, or UAMs, have low UMI ability. Their unstable dynamics, external disturbances, and strict stability requirements make them unable to reliably follow policy actions, even for simple tasks such as opening a cabinet. To measure this difference, we built a benchmark designed to test long horizon behavior, precision, and interaction with articulated objects. When we ran the same UMI policy across different embodiments, we found that the success rates dropped as UMI ability decreased, revealing what we call the embodiment gap. To close this gap, here's what we do. We start from a standard UMI policy formulation, which iteratively denoises action trajectories conditioned on visual observations. These action trajectories are then tracked by controllers, like MPC in our drone's case. Notice the one-way communication. The policy tells the robot how to move, but the robot can't tell the policy whether the movement is realizable. Our key idea is to enable two-way communication between the policy and the robot embodiment, and here's how we implement it. We can take the gradient of the MPC's tracking cost with respect to action trajectories. This gradient tells us how to change the action to make it more feasible for the controller. We incorporate this gradient as diffusion guidance at every time step. This steers the diffusion process, enabling two-way communication between UMI policies and the deployment embodiment. This is our approach, EADP, or Embodiment-Aware Diffusion Policy. Here you can see the difference. For the same observation, a standard diffusion policy proposes trajectories that are difficult to track, while EADP identifies modes with lower tracking costs for the embodiment. Or to put simply, EADP helps close the embodiment gap across our benchmark tasks. In real-world trials, the difference is clear. With a standard diffusion policy, the aerial robot drifts, misaligns, and ultimately fails to insert the peg. In contrast, with EADP, the system succeeds in all trials. This embodiment-aware correction dramatically improves precision and robustness, turning fragile, failure-prone behavior into a reliable, repeatable skill. We also tested in completely unseen environments. Here, the aerial robot successfully performs peg and hold in a scene it has never encountered before, demonstrating strong generalization. Importantly, the demonstrations used to train this policy were collected across the country with no access to the hardware itself. Yet they transferred directly to the drone, highlighting how UMI-on-Air enables scalable data collection and deployment. EADP also enables robust pick-and-place behavior. Notice how the robot grasps the lemon, slips because it's too difficult to pluck, and then regrasps, demonstrating recovery behavior learned from data. With UMI, it's easy to collect such recovery demonstrations, allowing the aerial manipulator to autonomously harvest ripe lemons and then place them into the basket. In one of our most challenging tasks, the robot autonomously installs a light bulb and then flips the switch. Over several minutes of continuous execution, EADP maintains stability and precise alignment, even as small disturbances accumulate. This is UMI-on-Air. This work moves us closer to making all robots more UMI-able, extending manipulation skills to embodiments and environments previously beyond reach. Thank you, and visit the UMI-on-Air website to learn more details.